We're going to start a new chapter today, chapter 13, and look at gases. So we can solve that problem that I accidentally added to the review last time and had to delete. So for this chapter, I've got 3 documents for you in Brightspace: the PowerPoints, the review document, and the work problems. No extras, just those. All right, any questions, problems we need to deal with before I get started? All right, if not, let's take a look at gases. Let's see. Well, it's a preview. We'll go to acids and bases next. For chapter 13, we'll have a review Thursday, and then a week from today will be the exam on this chapter. Since there's only one chapter, that's all the time we need. And then we'll look at redox reactions, which probably don't mean anything right now, but it will. That one we're not going to get to. This one was, I thought when I first started teaching this class, I thought we might get to that one, but there just wasn't enough time. So don't pay any attention to that one. We'll look at gases. All right. The usual outline. We'll get to all these topics today. Okay. Why in the world would we want to study gases? Well, historically speaking, in terms of modern chemistry, gases come first. In other words, what would become modern scientists, chemists, physicists, which at the time were called natural philosophers. They were basically jacks of all trade. But they began their studies. Now, this is after the alchemists. The alchemists of the Middle Ages, they were sort of glorified cooks. But I'm talking about modern chemistry. When modern chemistry started to develop, the first phenomena that were investigated in a scientific sense were gases. And there were a number of reasons for that. Well, if I stick to my slide, they were a good place to start for investigating the real world in scientific terms. In other words, make an observation, propose a hypothesis for why or how something happens, then conduct experiments and evaluate your results, and then circle back around and keep doing that until you gain a good understanding of the natural phenomena. Well, the study of natural phenomena at that time, which was middle 1500s, early 1600s, the technology allowed for this type of investigation for gases first. An investigation of liquids and solids had to come later, and even some of the things that were determined relative to gases required more advanced technology, and I'll make that this point several times during the lecture. But science is supposed to tell us how things really work. Okay, the nice thing about gases was, and still is, that if you have a gas, many of the investigations that you do with that gas are transferable to other gases. In other words, the phenomenon doesn't care whether it's helium or carbon dioxide or water vapor. A gas is a gas. So that was an excellent place to start if you don't know anything. Okay, just go back to a definition of a gas. Of course, gases have no fixed volume and they have no fixed shape. In other words, they are confined to the vessel. Now, the vessel for laboratory purposes is exactly that. It's an enclosure of some kind to hold the gas in. In the natural world, the vessel can be the surface of a planet, right? And the gases are confined to the surface of the planet because of gravity. But they still don't have a definite shape. Another interesting phenomenon with gases is when we discuss mixtures, right? And a homogeneous mixture of anything is a solution. If you put two gases together or more, doesn't matter how many, you always get a solution every time with no exceptions. This confined gas presents evidence of its existence based upon the pressure that it exerts on its container, right? So, and in these terms, the surroundings are the container. So we know something's in there if we can measure a pressure. If you put a gauge into a port in a container and there's no pressure measured at all, well, it depends on your gauge, actually. If the gauge is absolute and there's no pressure, then you've got a vacuum inside. The other type of gauge is open on one end into the container, right, like this. But it's also open to the outside. So there's a little diaphragm in there that serves as the device for feeling the pressure of the gas inside. So if that diaphragm is exposed on both sides, pressure inside the vessel, pressure outside the vessel, and the gauge says 0, that means the pressure inside the vessel is the same as outside the vessel. So, for instance, if we determine the pressure outside is 1 atmosphere, then the pressure inside is 1 atmosphere. If the gauge says 0, okay? All right. Now hopefully we're gonna look at reasons for this phenomenon right here. Exerts pressure on its surroundings. Why does it exert pressure on its surroundings? Let's see if I can get this thing to work. There we go. Right, see that better. Exert pressure on its surroundings. Okay, so I used the term pressure, but I didn't find what it meant. We sort of assume that pressure is some type of force. And that's true, but it's a special condition of force per unit area. Right? So the force that's applied and in SI units, force is in newtons. Right? So if we apply that force over a standard unit for an SI unit for area, that would be a meter squared. Okay, so 1 Newton per meter squared is given another value, and it's probably coming up in the slide later, but I'm going with it here. This 1 Newton per meter squared is equal to 1 Pascal. Those are standard units of measure in the SI system. Now, you need to know these so that if you have a calculation at some point in the future, you need to know what is this equal to. If you have this times something else, then it may not cancel out units unless you know that this equals that. Then you might cancel newtons, or you might cancel square meters, or whatever the case may be. It's important to know what these units mean in mathematical terms for calculation purposes. Now, for most of our calculations, we're going to use for pressure the units of atmosphere. So we need to draw comparisons here. All right. So the other point I need to make is that pressure is an intensity factor. Right? It's an intensive property as opposed to a capacity factor or an extensive property. Right? Remember, extensive properties change with the amount of substance, whereas intensive properties do not change, like density. If I have this size bowling ball, it has a certain density. If I have this size bowling ball, a kid's size bowling ball, it's got the same density, roughly. So this is an intensive factor, and most intensive factors are ratios. Not all, but most. The exception to that rule would be temperature. Temperature is intensive, but it's not a ratio. It's just a simple single unit measurement. All right, so there it is. Newton per square meter is 1 Pascal. What's a Newton of force, right? How do we relate newtons of force? Well, it goes back to Newton's second law of motion, right? If you haven't had physics or a physical science course, you probably don't know what that means, but I'm going to show you. Newton's second law of motion says that force equals mass times acceleration. So if you have a body that has a certain mass and you apply a given force to it, it will accelerate at this amount. Now, what's acceleration? Acceleration is a change of velocity. So acceleration would be velocity per unit time, right? And if it changes, then it's acceleration. All right, so you don't need to know that to pass a test, but it does help understanding what these things mean, right? This force unit, the Newton, anything in newtons in this force unit is related to standard or fundamental SI units. Mass is in kilograms, right? Kilograms. Acceleration, well, first, velocity is meters per second. Those are standard units. But meters per second, right? If velocity changes over time, then we have an additional time factor in there. Velocity is meters per second. Velocity per second is meters per second squared. Okay. So I said all that to say this: 1 Newton is equal to 1 kilogram meter per second squared. That's what this means right here. So if you need to make unit conversions, now you know what they're equal to. And in a calculation, you may have to know that. All right, so back to pressure. Pressure is a force per unit area. But the use of these units had to wait for the SI system to be developed. Preceding that, units of pressure were related to a device that was invented by an Italian fellow by the name of Tortellis, called the barometer. And I've got a couple of slides, I think, on that. But the barometer relates to a measurement of 1 atmosphere. Right? Some standard that's agreed upon 1 atmosphere. Now, there's a case where the atmosphere is not a ratio, right? Like newtons per meter squared. It's just 1 atmosphere is a pressure unit, kind of like temperature. But we can relate the unit of atmosphere to pascals. We know that 1 standard atmosphere is equal to 101,325 pascals. All right. And remember, anytime we have an equivalence, you have a conversion factor. And I showed you in earlier lectures how to make an equivalence into a conversion factor. Right? You just make it into a ratio that's equal to 1. All right. So these are other units of measure for pressure. Okay. 1 atmosphere we talked about. Right? And it's abbreviated ATM. And in Tortellis Barometer, the 1 atmosphere is equivalent to 760 millimeters of mercury in a column. And I'm going to show you a picture in a second. But in honor of Tortellis, 760 millimeters of mercury is also 760 torr. They're synonymous. All right. So this Italian physicist and mathematician invented the barometer in the middle 1600s. All right. Okay, just a side note. The Pascal, where did that unit come from? It's named in honor of this fellow right here, Blaise Pascal. He lived in the same century as Tortellis. I'm not sure if he was older than or younger than, but he was a French mathematician and physicist, and all of his experiments were with fluids. When we say fluid, we mean either a gas or a liquid. For our purposes, that's good enough. There can be other types of fluids, but they just flow. Okay, here's Tortellis barometer. So how did he make a barometer? Well, I mentioned earlier the limitations of technology on the investigations of natural phenomena. And one technology that was very well developed at this time in the middle 17th century was glass blowing. We had technicians, master craftsmen who could make things out of glass, and they were very good at it. They could make these tubes here, glass tubes of uniform diameter and straight as an arrow. So all Tortellis had to do was get one of those tubes that was long enough and seal it off at one end. And the other end, submerged in that vat of mercury, is open. So he took that tube and he poured mercury into it until he got right to the top. And he put his thumb over it. They didn't know about mercury poisoning in those days. Besides, mercury metal is not really as dangerous as they say it is. Organic forms of mercury are deadly, but metallic forms of mercury you get them on your hands and no big deal, as long as you don't have a cut. You don't want to get it inside your body. Of course, you don't want to drink it, and you don't want to breathe the vapors. But Tortellis put his thumb over that tube and then inverted it and submerged it in the vat, the container of mercury. And what happened? Well, The mercury was up here, and then it dropped to there and stopped. Okay? So, two things Tortellis had done. He created the first vacuum. Right? If you have space and it's got matter in it, and then all that matter is removed from that space, what's left? A vacuum. Nothing's there, essentially. Right? The other thing he noticed was that the column of mercury did not descend all the way to the level of mercury in here. Something is holding that mercury up. He knows mercury is heavy, right? So what has enough force to hold that mercury up? Well, there's nothing pushing on it down here that he could see physically. So it must be that something is pushing down on this mercury and transferring that force into the column. And he reasoned that that force was being supplied by the atmosphere. There was air above us, and the air has mass. And however much air is above you is bearing down on each square centimeter of the surface of that mercury with a given force. And it's being transferred into the column to hold that mercury up. Okay? So, the next thing he did, let's see. Yes. That's a good question. I was just reading my own question at the bottom. How could Tortellis be sure he was measuring an intensive property rather than an extensive property? Was he measuring force per unit area or total force bearing down on that container of mercury? Think about it. How would you do that? Well, if pressure is force per unit area, then if you increase the size of your container and you are measuring total force holding that column up, as you increase the size of the container, the column ought to go up higher because there's more force, right? Okay. So I'm not sure if he did that, but that's the way you would solve the problem. The size of the container didn't matter. So he knew he was measuring force per unit area. He was measuring a pressure. I don't know what the Italian word for pressure is. Okay. So before we get to this slide, he and other scientists, because the essence of modern science is to publish your work, distribute your information. If I find out something new, I let other people know about it so that they can build upon my work. And of course, I build on others' work to get where I am. It's really a group effort. So others used his technology, and he did too. And if you throw your barometer in the back of an ox cart, you go up a mountain, you'll notice that the level of mercury drops. So this is confirmation for his idea that the atmosphere has mass. And the higher you are up, the less atmosphere there is above you, which means less mass pushing down on your barometer. And if you go down to sea level, or even go below sea level, you'll see the column of mercury rise. There's more air above you bearing down on your barometer, forcing a higher column. So you can measure the pressure of the air relative to altitude. And all airplanes have altimeters in them. They tell them, what's your altitude? The altimeter, it can be one of two types. if it's not GPS using a satellite network, then it's based upon air pressure. So when you land at an airport, like land out here at Raleigh County Airport, then before you take off, you check with the tower for the current barometric pressure. And you set that into your altimeter. And that relates to the known altitude for your position. And then when you go up, it's going to show your increasing altitude based upon that barometric pressure that the device reads. Okay. Let's see. Weather. Some scientists were interested in weather forecasting, and they noticed if they just sit the barometer on the desk and just watch it day after day, they could correlate the air pressure with weather conditions. So if the weather was starting to get worse, like rain, thunderstorms, bad weather, the pressure would drop. And after the storm passed, the pressure would come back up, and then it might even go higher as the weather begins to improve. And we still use that today. High pressure, low pressure, you'll see it on weather maps anytime you watch the news. Okay, another use of this technology, and this is relative to gas pressure, is the manometer. The manometer is a barometer that is connected to a closed vessel. Okay. So if we want to measure the pressure of a confined gas, we need a manometer. It's a device that uses Tortellis principle to take the pressure of the gas bearing down on this column of mercury, and the difference between this level and that level is the pressure of the gas. Now, the other thing you have to realize is that you're not just measuring against the pressure of the gas, but you're measuring the pressure of the atmosphere also. So the atmosphere is pushing down on here, and if this side is lower than that side, what does that mean? That means the pressure inside the container is less than 1 atmosphere. 1 atmosphere will drive this column up against the opposing gas in that container, which is at a lower pressure. It has to be. The other possibility is the pressure is higher inside the container than the atmospheric pressure, and the difference in the two positions, the height of that column, is in addition to atmospheric pressure. Right? So the pressure inside the container is whatever the pressure is there, plus the pressure of the atmosphere. So you need a barometer and a manometer to accurately measure the pressure of a confined gas. Okay. Oh, before we go to this slide, there's one other pressure measuring device that is that anyone who's going into the medical profession is familiar with. It's called the sphygmomanometer. It's an extension of the manometer used to measure blood pressure. Right? You have a cuff that you wrap around the patient's arm, and you inflate a gas bag inside. So the device, the gauge, is measuring the pressure in the gas bag. Well, your heart's beating, and it's pushing against that gas bag. So when it contracts, when your heart contracts, pushes more blood into that artery, it forces against the gas bag, and you measure that pressure in your gauge. But other things, interesting things happen. You see the needle popping like that because your heart is beating, right? The pressure goes up, back down, up, back down. All right. So that manometer is connected to the armband that is a direct measure of the pressure in your arteries as they pulse. So why do we go to high pressure and then let the gas pressure out gradually? Well, we owe that method to a guy named Korotkov. Korotkov noticed that when he put a stethoscope near the cuff, he could hear various sounds. And he identified, I think, 5 different sounds. We're only focused on a couple of them to measure blood pressure. And as you let the pressure out, you'll notice that you reach a point where you get this large whooshing sound. And at that point, you look at your gauge, that's your systolic pressure, the high end, the high pressure. And then you listen and keep listening. There are other sounds that Korotkov identified, but we're only interested in when they disappear. So when the sound disappears, you read the gauge, that's the low pressure, the diastolic pressure. Okay? So this technology is, in fact, many doctors' offices still have sphygmomanometers that are based upon the mercury barometer, right? They're on the wall. They have to be stationary on the wall, and this long tube that comes out to fit around your arm. And you watch the mercury bounce up and down. Most doctors' offices don't use them anymore. They're there for decoration. Now we have the manual type. If you like, you can set it up so that you actually listen and measure it yourself. And then we have devices that you just wrap it on, turn it on, it pressures up, comes back down, spits out a number, 2 numbers, systolic over diastolic. I like the one where you do manually. I don't think those devices are always accurate. Okay. So, how do we know that there is air pressure? Well, the barometer tells us, right? But we can confirm that. All we have to do is create a vacuum inside a tin can, and it will collapse, right? Because the pressure outside is greater than the pressure inside, and it exceeds the structural integrity, the strength of the can, and crushes it. So how do you make a vacuum inside a can? Well, just put a little water in. Doesn't take much, a little water in the bottom, and heat it up. Right? Heat it up right there until you see steam coming out the top. Right? The cap's not on it yet. And you let it steam for a few minutes to be sure that you've got all the air is kicked out. Nothing in there but water vapor. Right? Then you put the cap on it. Use gloves because it's going to be hot. Put the cap on it, move the flame away, turn the flame off like this, right there. Okay? And then as the can cools, what happens to the water vapor? It condenses. The water vapor condenses back into liquid. And what does it leave behind? It leaves behind a vacuum or a near vacuum. So now you crush your can. My dad used to do this demonstration for his kids in 8th grade science every year. It was a big ooh-ah demonstration, but it was proof positive that air has pressure. All right. Okay, so if we're going to convert, which we need to do, right? Dimensional analysis again, that evil pair of words, unit conversions. The pressure of gas is measured as 2.5 atmospheres. Doesn't matter how we got the measurement, this is a problem, theoretical problem. Change this pressure from 2.5 atmospheres to torr and then into pascals. Okay, so what do we need? All right, where we're going? We're starting with 2.5 atmospheres first we're going to torr, which is millimeters of mercury. So that's what we know. And what we need is an equivalence to give us a conversion factor. All right. So our equivalence is 1 atmosphere equals 760 torr. That was on a previous slide. So we can create this conversion factor. And remember, all conversion factors are equal to 1. So we can flip it either way. However, we need to cancel atmospheres. So atmospheres goes on the bottom, torr on the top. And that gives us 1.9 times 10 to the third torr is 2.5 atmospheres. All right, so how about pascals? Well, we just need a conversion factor. How many pascals per atmosphere? That was on a previous slide. And there it is. Cancel atmospheres, 2.5 times 10 to the 5th pascals, rounded off to 2 significant figures. 2 significant figures. Even though this one's got, actually, conversion factors have infinite significant figures, right? They're exact numbers. All right. How about this one? So if you measure the vapor pressure of water over a beaker of hot water, and how would you do that? Well, if you had your beaker, that's a pretty lopsided beaker. Let's try it. Yeah, that's better. Okay. So if you have your beaker and you have water in here, then how do you know the pressure inside of the vapor pressure? It has to be enclosed. It has to be sealed. Now you have a pressure in here, a vapor pressure. Right? So we measured the vapor pressure in there with our manometer and found it to be 656 torr. So what's that pressure in atmospheres? Well, let me see. Do I need to do that one, or is it going to be worked out for me? Oh, it's going to be worked. Okay, so I don't have to do it on the board. So there you have 656 torr. Our conversion factor cancels torr and leaves us with atmospheres. Right? It's same as always. So we have 0.863 atmosphere inside the vapor pressure there. Okay. Now let's look at the results of some scientific investigations. And they're going to give us a set of laws, right, that pertain to gases. And remember, laws just say, this is what happens. I don't have a clue why. Or I'm not at liberty to divulge why at the moment. In other words, if I say why, I better have the research to back it up. Right? So at this point, we're talking about what happens. They're describing gas behavior. And the first one to do it in scientific terms is Robert Boyle. He was a contemporary, actually, of Tortellis, only he lived in England and Tortellis lived in Italy. But information was disseminated widely over the European continent. And it wasn't long before England got word of this new device called a barometer. So Robert Boyle got hold of it and said, aha, now I know that I can measure pressure, the pressure of a gas confined in some vessel. What I want to know is what happens for that, in that confined gas, what happens to its volume if I change the pressure? All right. So let me preface all of our gas laws with this statement. If you want to completely describe the physical character of a gas, I'm talking about chemistry, just the physical character, you need 4 measurements. You need to know the pressure, the volume, the temperature, and the moles. How much is there? Okay. So the reason I tell you that is, in order to investigate, as Robert Boyle did, the relationship between pressure and volume, these are the 2 variables. These have to be constant. They cannot change. Right? So when Robert Boyle was doing his experiments, measuring pressure versus volume, he had to be sure that the temperature was constant. And for these experiments would take minutes to do. So he's pretty sure the temperature was constant. If he wanted to be absolutely sure, all he had to do is submerge his device in ice water. And they knew that ice water would be constant temperature. They weren't real good at measuring temperatures at this point, but they knew that it would change. Anyway, constant temperature and constant number of moles. How much gas is confined, and you can't change the amount. The amount of gas you start with is the amount of gas you end with. So the way Robert Boyle did it was, he used this technology of the uniform diameter tube, only he had his glass blowers bend it into a J. Instead of a straight tube like a barometer, Boyle had his tube closed at one end on the short end here and the long end here. And all he had to do on it with his J tube was put mercury in it. So he put mercury, a little bit of mercury, and it cooled up in the bottom. Okay? We're not there yet. Put a little bit more in. Okay? When he put enough into it so that it touched the inner curve, now he had, that gas was trapped. There was not going to be any more gas put in, no gas would leave. So he met this condition by trapping the gas in that short end of the tube. And then he just kept adding mercury. What he noticed was, this side gets higher, but this side doesn't increase as fast. So he reasoned that the pressure on this gas in that container was the difference between these 2 levels. Okay? That represented his pressure, and it was in millimeters of mercury. But he was also smart enough to realize that this end is open. And what else is pushing down here? Atmospheric pressure. Atmospheric pressure. So this amount of mercury plus atmospheric pressure is the total pressure on that confined gas. And he did this stepwise. He added a little bit, measured that distance, plus this, and then he measured this one also. So this would be the volume of the gas. Now, these tubes were uniform diameter, so you could calculate the volume if you wanted to. Or since they were uniform diameter, remember the volume of a cylinder? Is area times height. So if the diameter here is constant, then the area is constant. So really, a measure of the volume of the gas is related to height. So he could just use height as his measure of volume, the height of the gas column. The height of the mercury column would be plus atmospheric would be the pressure. So he just laid out these. Let's see, do we have that? Let's see. Yeah, I've said all that stuff. And that's just if you want to calculate the volume inside that trapped gas in the tube, all you need is this length here times excuse me, here we go, times the diameter squared times pi divided by 4, and you have the volume. So you could do that if you wanted to. Okay, so this is not one of Boyle's tables, right? We made this one ourselves. But this is what he would have done in each experiment. He has added more mercury, so he gets a different volume, and he just lists it, right? Pressure here and volume here. And what he noticed was when he multiplies these two numbers together, he gets a value. And if he does it for every experiment, as he increases the pressure, the volume decreases, and the product of those two is not exact, but within experimental error, we might say they're constant. So Boyle's law says pressure times volume equals a constant value. And if you round them off to 3 significant figures, you can call that a constant. Okay, this is Boyle's law. Whenever you have two variables and you multiply them together, the product of those two variables, the values of those variables, equal to a constant, if that's true, then they are in an inverse relationship. Mathematically speaking, if this one goes up, that one has to go down in order to keep that constant. If they both go up, then the value changes. You don't have a constant anymore. So that's why we say they're inverse. If the product is equal to constant, they're inversely related. And we can graph those. Let's see, we're going to graph them. So if we graph those values, if we put the volume down here, actually, well, this is okay for illustration purposes, but mathematically speaking and experimentally speaking, which value did the researcher change? The researcher changed the pressure. The pressure, that's the independent variable, the one that the researcher changes. The dependent variable is the one that he observes in response to the independent variable's movement. So we always put the independent variable on the x-axis. So that's why pressure should be here. And then volume should be on the y-axis. But you'll get the same shape of curve, whichever way you do it. And notice the shape of the curve is, if you carry it on out, let's see, here we go. If you keep going out here, just keep going as the pressure decreases, the volume increases, you'll find that that curve never touches the axis, ever. And if you go this way, where the pressure increases and the volume decreases, the curve will never touch the y-axis either. So what do we call that in math? That is a hyperbola. hyperbolas behave that way. This is a physical example of a hyperbola. Now you can also look at it mathematically speaking, right? If the pressure goes so high that the volume decreases to 0, what would that do for K? That would change K to 0, wouldn't it? Right? Can't have that. Right? Or if the pressure goes so low that the volume increases to whatever, and the pressure goes to 0, which would mean touching this axis, right? It goes to 0, you have to touch that axis. Then this quotient, product, would also be 0. And that can't happen either. So mathematically speaking, graphical representation, they never touch the axis, and it is a hyperbola. All right. So let me make some more room here. Inverse relationship, yep. The line is sloping to the right from high to low, right? When we say the slope of the line, we say it's going to do that. The slope of the line is actually the slope of the line that's tangent to the line at that point, so it would change. That slope would be different than this slope, but it's always negative. A negative slope goes from high to low, left to right. Positive slope goes low to high, left to right. Right? If you remember your algebra and straight line equations. Okay, negative slope. All right. Now, if you are conducting this experiment yourself and you have a set of data, pressure and volume related, and then they're multiplied together and give you a K value that you determine by averaging all the Ks for each of the experiments, then you can take that information, and for that particular experiment, you can solve the equation, right? Because you have P times V equals the K that you determined, right? So if you know this now, then you can say, well, if I know volume is this, then I can solve it for P, right? It's like any equation. If you have one unknown, you can solve it. The problem is, suppose I don't want to have to calculate that K. Suppose I know the conditions before, pressure and volume on that gas are these values, and then I want to change the pressure, say increase the pressure. Now what's the volume? Right? Why do I need to calculate the K? I don't. Because that same experiment where temperature and moles do not change, these are the initial conditions, and then these are the final conditions. But notice, they're both equal to the same K, right? And that's a mathematical principle. If A is equal to B and B is equal to C, then A has to be equal to C. So if these two are equal to K, then they're equal to each other. That's where this equation comes from. P1, B1 equals P2, V2. Sometimes I call that before and after. If you know the before conditions and all but one of the after conditions, then you can solve for the other after condition. So that's another form of Boyles Law. All right. This is just an illustration. Right? If you increase the pressure, you decrease the volume. Right. So, how do you know if you're given a word problem on a test, for instance? How do you know you have you are able to use this before and after equation? Well, you look for the existence of constant temperature, constant moles. Pressure is allowed to change, volume is allowed to change. That tells you it's Boyles Law. Then, if you're given pressure before and pressure after, volume before and not volume after, it wants you to solve for that volume. You know it's before and after. So you have two of each. You have two pressures and two volumes. One of them may be unknown. And that's how you solve the equation. So in order to solve it correctly, it's a good practice to get into to say P1, V1, P2, V2, like that, and extract your information from the problem and put them in here so that you put them in the right place in the formula. If you put them in the wrong place in the formula, you get the wrong answer, obviously. So a sample of helium gas occupies 12.4 liters. Okay, at 23 degrees C temperature. Okay, and 0.956 atmospheres. All right, what volume will it occupy at 1.2 atmospheres? So we're increasing the pressure from here to here. What's this one? Now you have all your information out here in its proper place. You can plug it in the formula and get your answer. There you go. And notice by canceling these, we know that we're left with liters, which is a volume measure. So that's confirmation that we put things in the right place. Okay, so 9.88 liters. Now, does that make sense? Well, this is about 1, so that's around 12 and a half, maybe 12. And this is 9, almost 10 times 1.2 would be 12. So yeah, multiply these two together, multiply those together. They're pretty close. So that's an estimating check on your math. All right. So let's see, where are we going with this one? We're still pressure, no, we're a new law, okay? Charles' Law, that was Boyles' Law. We still have those 4 conditions. Now we're looking at Charles' Law. Charles was a Frenchman. So it's not unusual for the French to have a first name on the tail end. They get things backwards a lot. But what Charles was working with was volume and temperature. So he wanted the relationship of these two. There. That means this one has to be constant. This one has to be constant. Now, Charles came along later than Boyles. He was in, let's see, the early to mid 1700s, right? 70 or 80 years after. The reason Charles was able to do this experiment relating volume and temperature, volume was easy to measure. It's been measured forever. But temperature, a reliable, reproducible measure of temperature was not available for Boyles. There were various types of devices that were proposed, right? They had these little balls in a liquid and they see them move up and down. Let's see, what do they call those? Archimedes thermometer? No, that's not right. Anyway, but they weren't accurate enough for the type of work that Charles wanted to do. So what they needed was a thermometer and a measuring and a unit of measure that could be reproduced anywhere. All right, so two systems came into use. Fahrenheit first, and I think we mentioned this early on, and Celsius. And then the modification of Celsius was Kelvin, right? So once we need it, I'll explain it to you. But what Charles noticed was that as you increase the temperature, you also increase the volume, right? So what does that mean? Well, with a line that's a slope to the right and getting bigger as you go to the right, that's a direct relationship. And Charles's expression for that was volume over temperature equals a constant. Notice that when you have a quotient of two variables equal to a constant, they are directly proportional. Right? If this one gets bigger, that one better get bigger too to keep this constant. If this one got smaller as that one got bigger, then it wouldn't be constant anymore. Right? So mathematically speaking, this is always the relationship of a direct proportion, a quotient equal to a constant. Okay. Line is sloping to the right, which is positive slope, lower left, upper right. Let's see. Just occurred to me that we left Boyles Law. Oh, okay, never mind. We're going to get to it. We're going to come back to Boyles in a few minutes with a transformation. So just set that aside for now, and we'll get the other gas laws presented, and then we'll come back and talk about the Boyles again. Okay. So how did Charles keep these two constant, right? Well, if you have a vessel like this, and you put a piston in it, okay, now the gas is trapped. You have your gas in here with a given volume, and then you put a weight on it. Right? You have atmospheric pressure, of course, but if you put a little extra weight, like 1 kilogram, then it'll sink to a certain level. Now you have a constant pressure on that gas. Right? The force over this area, the area doesn't change, so the pressure is constant. That's constant. The number of moles is constant also because you trap the gas and you're not going to let any gas in and none can get out. So now we have constant. Now, how about the temperature? Well, the temperature, you can measure the volume easily, right? You just measure the height. But the temperature, you need something where you can measure the temperature, and you want your thermometer to measure the temperature of the gas inside. So one way is to surround the gas with some type of container and change the temperature of the surrounding so that the out of the gas. And once they reach equilibrium, then the temperature out here is the same as the temperature inside. Let's see. I didn't lose my connection, did I? Got a message? No, we're still connected. Okay. Good.
You're good.
So as long as you know the temperature outside and you give it enough time to equilibrate, then the temperature inside will be the same as outside. Now, whatever you do outside, you could pump in hot gas, you could make an ice bath, And then you could throw in salt and the temperature would start dropping, like you're making ice cream. So you can vary the temperature however you want within physical reason and relate that to the volume inside the container. Okay, so Charles also got a table of temperature and volume relationships, and he graphed them. And he got the, let's see, he got this graph right here. But notice that down here are negative numbers. This is valid for showing you the relationship, and these dotted lines means that wasn't part of the experiment. These are extrapolations, we call them. They go beyond the data, either this way or that way. So he also noticed that if this relationship was going to be maintained, he needed a unit of measure for temperature that was never negative. Because if you get down here, you go to zero, of course, zero, right? Mathematically speaking, what's anything divided by zero? Infinity, right? That won't work. He needed a number for temperature that was never negative. That's where the absolute system comes in. And Kelvin came up with that. I think I've described that before, right? Kelvin temperature equals Celsius plus 273. So all he had to do to make this formula work was to convert all of his temperatures to Kelvin. And now they're always positive. And remember that rule. Anytime we're working with temperature, almost anytime, but for this chapter, temperature, if you're going to do a calculation with temperature, it needs to be in Kelvin degrees. That's not right. Kelvin. There's no degrees with Kelvin. Celsius degrees, Kelvin is just Kelvin. Okay. So this way, if he ever was able to reach, theoretically speaking, zero volume, that would also be a point at which temperature was zero in Kelvin, right? So you can never go to negatives with temperature here. All right. Okay. Just a detail. Charles' law is named in honor of Charles because he did experiments. But his work and the additional work of Gay-Lussac were published in 1800, and Gay-Lussac gave Charles credit for his contributions to Gay-Lussac's work. And that meant that the law was in Charles' name, not Gay-Lussac's name. Okay. Let's see. We got 2 extra decimals out here. You don't have to use those when you're doing calculations. 3 is good enough. 273 is fine. That's the absolute zero. Okay. We use a similar mathematical progression for Charles' law to make it a before and after situation. Just like we did with Boyles, if this is equal to a constant before, it's also equal to a constant after. As long as we don't change this one or that one, then this relationship holds and this formula is valid. Okay. Let me see. How am I doing on time? I might need to go through this one pretty quick. Suppose you have a balloon that contains 1.3 liters of air. It doesn't matter what the gas is, like I said before. At 24.7 degrees Celsius, you place it in a flask, a Dewar flask, right? You probably never heard of a Dewar. You may have used one before, right? If you ever had a vacuum bottle, right? A thermos bottle, they call it. That's a brand name, thermos. Is a Dewar flask, is a Dewar bottle. It has an inner glass container and an outer metal container. And between the two is a vacuum. Right? So there's no heat transfer between the two. And you need that if you're going to be dealing with very, very, very cold liquids. So that's why we put it in a Dewar here. And then, let's see, you have this balloon that's this volume and at that temperature. Now you put it in a Dewar flask that contains liquid nitrogen at minus 195 degrees Celsius. What's the volume of the sample of air after? Right? The pressure is constant because it's open to the atmosphere. Right? The atmospheric pressure on the balloon is not going to change. But the temperature does change, and the balloon confines the number of moles of gas inside the balloon, so that doesn't change. So your before is 1.3 liters volume, and 24.7 plus 273 is the temperature. And then after, the temperature is 273 minus 195. And the unknown is V2, the second volume. So you can solve that one. There it is. There's your relationship, solving for V2. So the balloon has shrunk from 1.3 liters down to 0.3 liters. Oops. There we go. All right. The third one, the third law I want to discuss. Okay, and there are 4 conditions. This one relates volume and moles. Okay. So this one has to be constant. This one still has to be constant. And we're going to relate volume and moles. This is Avogadro's law. And simply stated, volume and moles, volume divided by moles is equal to a constant. Right? So you recognize that one, quotient equal to a constant, this is a direct proportion. So as the number of moles increases, the volume increases. And that's what this illustration is saying. With constant pressure, if we put more moles of gas in here, if the number of moles is 1 to begin with, and we put twice as much in there, then the volume will increase twice as big. Or if we put 3 times as much, the volume will be 3 times as much as the original. Avogadro was given credit for this work. He didn't actually publish it as that, but his published work led to this concept. And actually what Avogadro said, let me see, is this slide going to fill in the blanks for me? No, I need to say something. Here's what Avogadro actually said. He said, if you have 2 volumes of gas, they don't have to be the same gas, doesn't matter. The volumes are the same. This volume is equal to this volume. Okay, beginning conditions. if we maintain them at the same temperature, okay, and the same pressure, okay, we measure the pressure inside, it's the same for both of them, same volume, same temperature, then this one must be true. The number of particles, the moles of gas in this one is exactly equal to the moles in that. And it doesn't matter what gas it is. You could have helium in one and krypton in the other. The number of particles in each one is exactly equal. That was Avogadro's proposition. And it came at a most opportune time. In fact, let's get through this part. There we go. Now you can flip this over, which I've done here. And this is before and after. You change the number of moles, you change the volume. Before and after. Now, this is actually an extremely important concept for chemistry. We're talking the physics of gases here, but this translates into chemistry because during the chemical reaction, if the gases are involved, then the gas, you may have 2 moles of gas as reactants and then 10 moles of gas as product. Right? That being said, if you go from 2 to 10, you've increased the volume by 5 times if the pressure and temperature are maintained constant. Right? So Avogadro's work was taken up by one of his students, by a guy by the name of Cannizzaro. And Cannizzaro became a chemistry teacher. And before he started teaching, all the chemistry that was known in sciences at that time was related to mass of reactants, mass of products. So researchers in universities and engineers, chemical engineers in companies, if something went wrong in their reaction, it didn't come out like they expected, they were stumped. They had no idea how to solve the problem because they were approaching it from the wrong direction. They were approaching it from mass. Mass equals mass, which it does. Mass of reactants equals mass of products. But that doesn't solve the reaction mechanism. The reaction mechanism is based upon moles, right? And we learned that when we balanced equations, right? When you balance an equation, you have moles of this element, moles of this element, even if they're in compounds, they got to be equal on the product side. But they had no way of getting a handle on the number of moles in the reaction as it proceeded until Avogadro's principle, Avogadro's law. And Cannizzaro took that and worked it out. And he actually wrote a textbook that he used for his chemistry students. I'm trying to think of where he was teaching at the time. Florence, I think. I could be wrong. It was northern Italy. Anyway, all these scientists and engineers were having so much trouble with their reactions, they got together in a little southern Bavarian town called Karlsruhe. There was a college there. So they met at that college for a week or two and said to themselves, we're going to solve this problem. We get all the greatest minds in Europe together. We're going to solve this problem. Well, they didn't. Cannizzaro was there and he gave his talk and explained reactions in terms of numbers of moles. And he had published his work also. So he had reprints and he was standing at the door as everybody was leaving, handing out reprints. And they politely took the reprints and went back to their colleges and companies. And some of them read it and light bulbs went on all over Europe. Some scientists realized this is the solution to the problem. Now they know that if this mass is not equal to that mass, and there's the same number of particles in each side, then the difference in mass must be due to the individual particle difference in mass. So now they had a handle on how to relate masses of atoms and compounds. And they started solving their problems, to make a long story short. Okay, so that was Avogadro. And he was given credit for this law, even though Cannizzaro popularized it. Right, so this is a direct relationship. And we can solve a problem, right? I'm going to have to maybe even skip this one. 2.45 moles of argon gas occupies a volume of 89 liters. Okay, those are beginning before position conditions. What volume will 2.1 mole of argon occupy under the same conditions? So this is the after. This is the before. This is the after. And notice, when you have these ratios of P1V1 equals P2 V2, it doesn't matter what the pressure units are, doesn't matter what the volume units are. They're going to be the same on both sides. Volume in moles, right? Whatever those units are, they'll be the same on both sides. The only one that's really picky about the units is temperature. Whenever you have temperature, it must be Kelvin. But everything else can be whatever you want it to. And if it starts off liters, the answer will be in liters. If it starts off milliliters, the answer will be in milliliters. Because they're ratios, right? And they would cancel units. So the units don't matter except for temperature. So this is the solution for that problem. And we find that if you decrease the number of moles, you decrease the volume. Oops. Okay. All right. Before we talk about the ideal gas law, let's combine Boyles Law, Charles' Law, and Avogadro's law into a single unit, into a single equation. And then we'll go to the ideal gas law from there. So if we know that P1 V1 equals P2 V2, right? Boyle's law. Charles' law relates volume to temperature, right? So there's T1 and there's T2, right? Volume to temperature. If pressure is constant, then you have Charles' law. The relationship of Avogadro, discussed was volume in moles. So volume to moles is like that, like that. So if pressure and temperature are constant, you got Avogadro's law. But the beauty of this equation now is that you can have multiple variables. In other words, pressure can change, volume can change, moles can change, and you can know temperature before and calculate temperature afterwards. Right? So it can be more complex using this combined gas law. In fact, I don't believe I put that in here. No. Okay. I need to make an extra slide for that one. Okay. Now, this expression would be equal to a constant, right? We're going to go backwards now. Instead of saying A equals B and B equals C, we're going to say since A equals C, then A has to be equal to B and C has to be equal to B. And B is the constant. So if we substitute here, constant, right? That expression is constant for a given experiment. I'm headed for the ideal gas equation. And the reason we're doing this is because before and after, it may not always be your option. You may be dealing with a state function. In other words, this is where I am right now. I don't know how I got here. So this is how you solve that problem. If you're not given before and after information to use one of the individual gas laws or the combined gas law, then you can use the ideal gas equation. So if this expression is equal to a constant, all we need to know is what is that value. Well, that value depends upon the units of this one, that one, that one, that one. Okay? If we know what this one is, we give it a special symbol, R. And we rearrange it so that it's there. Rearrange that equation. This is what you get, and that's how you most often see it. PV equals nRT is the ideal gas equation. In this equation, if you know that and three of the others, say this one, this one, this one, and that one, you can calculate pressure, and it doesn't matter how you got there. But it does matter the units that you use. The units for each one of these is dependent upon the units for that one. And for our purposes in this class, we're going to use R equals 0.08206 liter atmospheres per mole K. Volume, pressure, moles, temperature. So that means pressure has to be in atmospheres. Volume has to be in liters. This has to be moles. This has to be Kelvin. If all of those conditions are met, then you can solve that equation from a state situation where you don't know before and after. You just know what is it right now. Okay. And there it is again. Right. Now, if you dip your toes in chemistry in the future, you may see different values for R. And it all depends on the units of measure and what type of experiment is being conducted. But R, it goes lots of different places. Okay, so for this one, we say an automobile tire is 23 degrees Celsius. So in that case, you have these conditions, 23 degrees Celsius, an internal volume of 25 liters, a pressure of 3.18 atmospheres. How many moles are in that tire? How many moles of gas? Right. All you have to do, we solve for moles first, and then we plug in the values, right? Atmospheres, liters, that's good. Liter atmospheres, that's good. Moles, that's going to be your answer. K. We have to convert the temperature to K. So we would say plus 273. And then solve for moles. Okay. 3.27 moles of gas is in that tire. And it doesn't matter what the gas is. It's just that many particles of a gas is in that tire. Notice This moles is in the denominator, but it's also in the denominator of the denominator. So mathematically speaking, that is the numerator. So that's why it flips over and shows up here in the numerator. Okay, let's see. We got another one. Oh, okay. What's the pressure in the 304-liter tank? So this method is helpful also to help you map out a procedure for solving the problem. We know that 304 liters is the volume of the tank, and it has 5.670 kilograms of helium. So we're given the mass, 5.670 kilograms of helium. And the temperature is 25 degrees. Okay. What's the pressure? What are we missing? We're missing moles. Right? Can we get moles? Yeah, fortunately. We know the mass and we know the gas. Okay. So, how do we convert mass to moles? Molar mass. The molar mass of helium is 4.00, but it's 4.00 grams per mole. So 5.670 is 5,670 grams. And then we would multiply that times 4.00 there. So divide 4 into that, and we get the number of moles. You just plug that value in here. And then we solve our equation for pressure. nRT divided by volume. This is, there we go. And I think that's what's coming. Yep, there we go. And it's kind of messy, but this one changes the mass of helium into moles, right? That's the N. There's your R. There's your temperature. There's your volume. And cancel the units. There's your pressure. 114 atmospheres. That is a lot of pressure. I hope that tank is strong. Let's see, 114 atmospheres. That would be the same as going down in the ocean 3,700 feet. If you went that deep in the ocean, you would have that pressure on your body or on your vessel. You wouldn't survive that if you weren't in a vessel. Or you weren't a jellyfish, something that was built for it. Okay. Let's see. We got another one. At what temperature does 121 milliliters of CO2? All right, I'm just going to set this one up. Temperature is our unknown. 121 milliliters of CO2 at 27 degrees and oh no, notice, threw me a curve. What we have here is a volume after and a volume before, a temperature after and a temperature before. a pressure before and a pressure after. This is a before and after, but there are several variables going on here. So we would actually need right? So we're going to keep the temperature, right? It changes. The pressure changes, okay? And the volume changes. How about the number of moles? Don't need them. Moles do not change. So we just set up our table, our list, so that we have the right values in each one of these and solve for the unknown. There we go. Here it is. So there's your P1 V1 over T1 equals P2 V2 over T2. And if you put the numbers in the right place and solve for the unknown, the temperature is 969 K. What's the temperature in C? Subtract 273. 696 degrees Celsius, which is pretty hot. Pretty hot. Okay. One more law. Dalton's law of partial pressure. Remember John Dalton, the atomic theory? Same guy. He came up with this one also. The law of partial pressures is very simple. It just says, if you have a gas mixture combined in a vessel, and you measure the total pressure inside that vessel, the total pressure is actually the summation of the pressure due to the individual gases. So if this gas produces that pressure, and this gas produces that pressure, and this gas produces that pressure, the total is the summation of each of those partial pressures. And this can go out as far as you need it. There's no limit. All right. The pressure inside the vessel is dependent upon the number of particles. Right? So if we take this gas out, then the pressure will decrease because we've removed particles. And goes without saying, the pressure is independent of the type of gas it is. It doesn't matter what the gas is. It only matters how many of them are there. Okay. This is just an illustration. With the same pressure, you can get the same pressure out of one gas under these conditions, or three gases under these conditions, where they sum up to the same number of moles, right? 1.75 moles of helium. You sum hydrogen, helium, and neon to be this number of moles. Under those conditions, same pressure. Or you change the mix of gases, as long as it's the same number of moles, then you get the same pressure. So this illustration is telling us that the relationship here is the same as the total number of moles to the moles of each of the gases. Right? So if you know the ratio of pressures of the gases, say on a fractional basis, the pressure of this gas is 0.3 of the total. Then this will be 0.3 of the total number of moles. Okay, that's a useful bit of information because it's easier to measure pressure than it is to measure moles. If you measure the pressure of this one relative to the total, you know that the fraction of the number of moles is related to the fraction of the pressures. Okay. Let's see. I'm going to have to skip this. This is a practical application of partial pressure. Hopefully we'll be able to do one of these when we review on Thursday. I'll just give you the particulars. You're conducting an experiment that produces a gas. In this case, it's potassium chlorate. When you heat it up, it decomposes into potassium chloride plus oxygen gas. And we can collect the oxygen gas in here. If we fill this vessel up with water, and then we bubble the gas in, it displaces the water, right? And we can measure the volume inside the container. And we know the pressure inside the container is the atmospheric pressure. And subtract the pressure of the water. What you try to do is you fill it up to the point where the water levels are pretty close. That means the total pressure is equal to atmospheric pressure. Well, what's the problem here? You just bubbled your gas through water, and it picked up water vapor. So now you have a combination. The gas in here is not pure oxygen. It's got water vapor in it too. So how do you separate the two? Dalton's law of partial pressures. You know the total pressure, and you know what the vapor pressure of water is at a given temperature. Subtract that from the total, you have your pressure of oxygen. And that's the short version. Okay. Let's see. And there's your table for the vapor pressure of water. All right, so if we have say room temperature, well, standard temperature is 25 degrees for chemical reactions. So we know that the pressure due to water is 23.756 torr. We just measure the total, and that gives us, and subtract that, and that gives us the pressure of the gas inside the container, the collected gas. Okay. Here's another. I'm gonna have to skip this one too. I'll be sure and do this one. I think it's one like this is in the review document. Right? How do you solve this problem? If you have a cylinder and connected flasks, right, with this valve right here, and the valve's closed right now. This side has a gas in it at 3 atmospheres and 3 liters. This one has 2 atmospheres and 9 liters. Right? So when you open that valve, what's going to happen? Well, the pressure is going to equalize, which means you're going to get this 3 atmosphere gas is going to move over here until the pressure is equal. Right? We want to know what's the final pressure. The way to solve this problem is to treat each individual side as if it were being expelled into a vacuum. And then you take those 2 individual pressures of each individual gas and add them together. And that's the total pressure. Okay? So this works out the problem in detail. And I'll just scroll through it slowly so that it's recorded. So you use Boyles Law to measure the final pressure before and after for the 2 atmosphere, 9 liter example first, being expelled into a vacuum. It contributes 1.5 atmospheres. Then you do the same thing for the other one. It contributes 0.75 atmospheres to the total. Add them together, using Dalton's law of partial pressures. So the final pressure is 2.25 atmospheres. Now, does that make sense? Well, let's see. The pressure can't be less than 2 or less than 3. It's got to be in between somewhere. Right? If this pressure is going to expel into this one, it's going to increase that one and decrease this one. So it's got to be between 2 and 3. And it is 2.25. Okay, let's see. Do we want to 27.4 liters of oxygen gas at 25 degrees and 1.3 atmospheres, and 8.5 liters of helium gas at 25 degrees and 2 atmospheres were pumped into a tank with a volume of 5.81 liters at 25 degrees C. What's the new partial pressure of oxygen? Well, let's see. Oxygen gas is the first one, and then helium gas. This has blue smoke in it. The helium gas, if the question is, what's the partial pressure of oxygen? It doesn't matter what the helium is. You can treat the oxygen independently of the helium. So you're going before, right? This is before for oxygen. This is after oxygen. Oh, it's asking for helium also. All right, so we have to do both of them and then add them together to find the total. So it's a similar problem as before. You treat them independently as if they're going in independent, and then you take the answers and add them together using Dalton's law, and that gives you the final answer where you have both of them together. This gives us the pressure for oxygen. This gives us the pressure for helium. And then you add them together, and that's the final pressure inside the vessel. Okay, this is a review. Let's see. Actually, there's a little more to go. The scientific method we've talked about before. Just a reminder, laws are useful, but they only predict behavior. They don't say why the behavior happens, right? So they're limited. If we have a theory, which usually is accompanied with a model, some type of either physical, mathematical, conceptual of what's actually happening, the whys for the law and the theory from which laws now are derived, then you use the model. Models are good because you can change the model and say, what effect does that have on the theory? Whereas a law, you can't do that. The law is just, it's chiseled in stone. It's this, and that. That's it. But with a model and the law that goes with it, you can make modifications and see what effect does that have on the outcome. Predictability, predictions. Okay, so now for the final theory that explains all these laws. It's called the kinetic molecular theory of gases. And it attempts to explain why things happen the way they do. I just clicked through that one statement. In the sciences, what happens nearly always precedes why something happens. We gather all the information we can about what's happening, and then we propose a theory and develop a model to explain why it happens. So laws usually precede theories. So these are the starting points for the kinetic molecular theory. And keep in mind, when we lay these out, the attempt is to explain why the gas laws work the way they do. Gases consist of tiny particles, right? That seems like a no-brainer. Atoms or molecules, whatever the case may be, very tiny, extremely small, relative to the volume that they occupy. That's the second point. They are so small that we can treat them as points, right? No volume. These particles are in constant random motion, right? Constant is fairly easy to deal with, right? If we've got a temperature, a measurable temperature for the gas, that means there's energy there. And energy means those molecules are going to be moving. The random part is out of necessity. We don't have the computing power and the ability to track the trajectory, the velocity, the mass of every particle in that gas. There are just too many of them. No supercomputer can do that. So we have to treat it as a statistical basis. Random motion. We just say there's moving randomly. Whereas we know that if two molecules come together at a certain angle, a certain energy, we can predict how they're going to act for one collision. But these are billions and billions of collisions per microsecond. So we say the motion is random. We also have to assume, at least in the beginning, as our starting point, that these molecules, when they impact one another, and they do, when they impact, they do not interact in any way except physically. In other words, they bounce off each other like billiard balls. Their collisions are completely 100% elastic. That is, the energy they come in with combined is the same energy they leave with. And there's no attraction, no repulsion involved whatsoever. Now we know that that's not true, but that's our starting point. The average kinetic energy of all the gas particles in your container is directly proportional to the Kelvin temperature. So you increase the temperature, you increase the kinetic energy of your particles. All right. Now, if we knew, and we could calculate for individual atoms and molecules, we can calculate their kinetic energy. All we need to know is what's the mass and how fast are they moving. Right? It's an easy equation to solve if you can get the information. That's the difficult part. All right, so as we increase the temperature, what happens in terms of the gas laws, right? Let's see, who was it? Charles. If you increase the temperature, you're going to increase the energy of each of the particles. So when they smack into the walls, what are they going to do? If the walls are movable, if the pressure is constant, then that plunger, the cylinder, is going to move up. The piston is going to move up because it's being hit by greater force as we add energy to the particles. That explains Charles' law. How about pressure and temperature? Well, if we hold the volume constant, this is not one of the laws, it's derived from the combined gas law. If we hold the volume constant, right, and increase the temperature, we're increasing energy of each of the particles, and they smack the walls harder with more energy, and that's measured as a force per unit area. We increase the pressure, increase the temperature, increase the pressure. All right, so I got 2 minutes to finish this thing, and I'm not there yet. Okay, if you have to leave, I'm going to finish this lecture. We've got a half a dozen or so more slides to go. But I don't want to skip this one. All right, we have two balloons of exactly the same volume. One contains helium and one contains hydrogen. In the subsequent slides, we're going to say, are they different or the same in terms of the question that's asked? So, the pressures of the gas in the two balloons are what? The same or different? They have to be the same. They're subject to the same external pressures, and they're the same volume. So they have to be exactly the same. There you go. All right, how about this one? The temperatures of the gas in the two balloons are what? If they're in the same environment, they have to be the same temperature. All right. But this one, the numbers of molecules of gas in the two balloons are what? Avogadro said, if the volumes are equal, the pressures are equal, temperatures are equal, the moles are equal. So the number of molecules in those balloons are exactly equal. Now, here's the kicker. How about the densities? What's the density? The density relates to the mass in each balloon. They're the same volume, so the only difference between the two, if their volumes are equal, the only thing that can vary to make the densities different is mass. Do we have different masses? Yeah. Helium is twice as heavy as dihydrogen. So the density for helium should be twice that of hydrogen. Right? They are different because they have the same number of molecules, and each molecule is a different mass than the other. Helium is a different mass than dihydrogen. Okay. Now, here's the pressure-volume relationship that I wanted to get to before. Remember when we had change the pressure, change the volume for Boyles Law, we get a hyperbola. Scientists don't like curves unless we have to deal with them. Straight lines are much easier to deal with. If there's a way to transform your data to give you a straight line plot, we're going to take it. In this case, we have pressure and volume are these values. As this one gets, let's see, let's start off at 10, and the volume is 1. And then we cut it in half, the volume will double. Cut it in half again, the volume will double again. All right, so as the pressure goes up, the volume goes down. Pressure goes up, volume goes down. Notice the relationship here. P times V equals a constant. What if we divide both sides through by volume? Right. We can do that. Mathematically speaking, do the same thing to both sides of the equation. You haven't changed it. Divide by volume cancels that volume, right? And leaves us over here. Well, that's also equal to K times 1 over V. Notice, pressure equals K times 1 over V. What does that look like? That looks like Y equals mx plus V. Straight line. If we take the inverse of volume, right, 1, 0.5, 0.25, and we plot this one against that one, we get a straight line, and the slope is K. Now, what's B? B is the y-intercept. Remember your math? B is the y-intercept. 0, right? There's no 0 here. I mean, there's no B out here. It's 0. So the slope is K, and Y is the pressure, and X is 1 over volume. That's how you get a straight line. And I think that's what this slide is trying to show you. That's Charles' law, volume and temperature. Volume and moles, that's right. Oh, I thought we were going to have a slide on this, but it's good information. Know how to make a straight line out of a hyperbola. Okay, what if the volume of the neon balloon is twice that of the argon balloon? What's the question? What's the mass ratio of neon to argon? Well, first of all, what's the number of moles? Well, the number of moles of neon will be double that of argon. You got twice as many moles of neon as you do argon. So each one of the neons weighs 4 grams per mole, and each one of the argons weighs, no, neon weighs 20. Neon weighs 20. Right? So neon is 20 and argon is 40. Right? So if you have twice as many molecules of neon as you do argon, then you've got twice the collective mass. So if you got twice as many neons, you've got 40. And if you only got 1 unit of argon, you got 40. So their masses are equal. The ratio is 1 to 1. Okay? All right. Let's see. Yeah, we're getting close. Not there yet. You have a sample of nitrogen gas in a container fitted with a piston that contained the pressure 6 atmospheres. Initially, the gas is at 45 degrees in a volume of 6 liters. You then cool the gas sample. All right. So you got the number of moles is constant. We got no way to get into or out of that. So the moles is constant. Pressure is constant at 6 atmospheres. So if we change the temperature, the volume changes. That's Charles' law. So if we're going to cool the gas, the pressure of the gas increases. No, the pressure is constant. Pressure is constant. The volume of the gas increases. No, if you're going to cool it, the volume will decrease. Right? So we can leave the pressure out. The volume of the gas decreases. Yes. Takes care of that one. So we're going to cool the temperature down to 15. What gas law we used? I just told you, Charles' law. And if we actually quantify these changes, then you can calculate the final volume. It decreases from 6 liters to 5.43 liters. Remember, we had to change the temperature to Kelvin in order to do that calculation. So what's the molar volume of an ideal gas? What do we mean by molar volume? What volume does 1 mole of gas occupy at standard temperature and pressure? So for gases, standard temperature and pressure is 0 degrees C and 1 atmosphere. Okay? And we're looking for 1 mole. What's the volume? Okay? Is this a before and after? This is a state function. We use the ideal gas equation. So we're solving for volume. Right there. So how many moles is it? 1 mole, 0.08206. And 0 degrees is standard temperature for gases only. For chemical reactions, the standard temperature is 25 degrees C. But for gases, it's 0. So that means 273. Okay. And then pressure is 1 atmosphere. So if we take all these values, right, 1 divided into it 1 times it, so it's really just this one times that one. The volume is equal to 22.4 liters. At standard temperature and pressure, 1 mole of any gas will occupy 22.4 liters. Well, for 2 decimal places, 22.42. All right. Let's see. Gas stoichiometry. Okay. Now we're getting to the place where we can solve that equation, solve the problem that I accidentally gave you in the last chapter. A sample of oxygen gas has a volume of 2.5 liters at standard temperature and pressure. How many grams of oxygen are present? This is dimensional analysis. 2.5 liters of oxygen. And we know the conversion factor. This is the molar volume of any gas. So this will give us so many moles, and then we know that 32 grams per mole is the molar mass of oxygen. And that calculation says we have 3.57 grams of oxygen. That's method 1. Method 2 is to use the ideal gas law. Right? There's our pressure. There's our volume. There's our constant. There's our temperature. This tells us the number of moles. Here. And now we just convert the number of moles to grams. And we get the same value. So in reality, the ideal gas equation is at the root of both of them. Both this one, obviously, and this one also, because we had to use the ideal gas equation to calculate that value, that conversion factor. So here's a reaction, zinc solid, hydrochloric acid. I put zinc metal and hydrochloric acid, you start getting the gas. Right? The reaction is you produce zinc chloride, which is soluble. It's an aqueous solution. But you get this gas given off. Okay. You probably see where this one's going. If you have 15 grams of solid zinc and react it with 100 milliliters of 4 molar hydrochloric acid, what volume of hydrogen gas is produced at 25 degrees in 1 atmosphere? Okay, so first of all, before we can calculate the volume of hydrogen, we need to know the number of moles of hydrogen produced. And that's a simple stoichiometry problem. What you have to do is, next slide, the equation's balanced. The amount of product, right, we say, I'm thinking that's how many moles of zinc we have available. And if we take that number of moles of zinc and say, this is how many moles of hydrogen can be produced from that zinc. If we do the same thing for hydrochloric acid, right, using what we know about solutions, this is a limiting reactant problem. Find out which one is the limiting one. Right? So this one calculates 0.4 moles of HCl, and we convert that to hydrogen. There. We find that the limiting reactant is the hydrochloric acid. So this is the most that you can produce, 0.2 moles of hydrogen. Now, we want to know volume. Right? So do we have the information we need? Well, we got moles. We got pressure, PV equals NRT, right? The ideal gas equation. And that solves for volume, right here. So we're going to collect a volume of 4.89 liters of hydrogen under these conditions of 1 atmosphere pressure at 25 degrees Celsius. Oh, here it is. Okay, so this explains the straight line conversion of Boyles Law. I did it on the board before, but this puts everything in a cleaner format. Okay. That's it.